Oh, hey, didn't see you there. I was too busy reading these math jokes like this one. Why did the decimal win the debate? Well, it was because he made a good point. Or maybe this other one that I read. What kind of triangle loves to skate? Well, of course, it would be an isosceles triangle. Welcome. It is Calc time with Miss Wesley. Today, before we embark upon a new unit called L'Hopital's Rule, we're going to refresh what we know already from our very first unit of calculus, which was all about limits. So I have this throwback limits review sheet. Zach and Cody are here. They're looking a little bit skeptical, but we're ready to solve some of these questions. And I feel like let's skip around and see what we remember about finding limits visually from a graph and then also algebraically, just looking at an expression. Check out number one. If I told you to look at number one and tell me about the continuity at x equals 1, I would hope that you would tell me there's a little gap in the graph here. And what that means is you have what's called a left-sided limit, and you've got a right-sided limit as well, but there might not be a limit as a whole. So let's look at what this question's asking. It says, can you find the limit as x approaches 1? Remember that little -1 subscript, negative subscript, means from the left. And I'll slide down the function from the left, stop when I hit this x value 1, and I'm going to say my left side limit's up at 2. Now this wasn't technically asked for in the problem, but maybe we can take that one step further. What's the limit as x approaches 1 from the right? Well, if you recall, I start at the far right of the graph, walk up the function, stop when I hit this x value 1, and I'm not quite up at 2, I'm down at the y value 1. Here's a case where the two one-sided limits do not agree. That means if someone's asking us for the limit as x approaches 1 from both sides, we can't give them any answer. We're going to say it does not exist. There's a jump discontinuity at that spot. And if we skip down the page, if we look at 3, we see there's also a different kind of discontinuity. 3 looks kind of like it, but this one, the two sides do connect just at a whole, at an undefined value. If somebody asked me what is f of 1, from this picture, I would have to say there is none. There's an open circle there, meaning the lack of a point, so it's undefined. However, limits, right, they care about what's happening at the approach to that value, so there is a left and a right-sided limit, and I believe a limit as a whole. Let's write it down. So limit as x approaches 1 from the left of f of x should equal the same thing as the limit as x approaches 1 from the right of f of x. And that equals both times the number 2. You're approaching 2 from the left as a y value, 2 from the right. And if these two one-sided limits agree, we're going to say the limit as a whole. Let me write this out. Limit as x approaches 1 from both sides equals 2. So I love having a graph or a table in front of me to visually kind of look at what the two sides of the function are approaching around that x value. Now we get to the fun stuff, right? I like these because we can use some algebra. There is, if I look at 5, there is an easy way to get a limit. If you don't see any problem with just some direct substitution, just plugging in the 1 for x, I say go for it. For this one, I don't see any problem with just plugging in 1 for x here and 1 for x inside of the parentheses and simplifying this answer. So I'm going to get 1 times what? 0 squared, which is just the number 0. If we looked at a graph or a table for this one, we should see the two sides of the function approaching 0 as you get to 1, get closer and closer to 1 from the left and the right. But then, of course, they're not all like this where you can directly substitute in. I'm looking at 6, 7, and 8, and in all 3 of these, I see a problem with plugging in the given value. Let's look at 7. So 7 says, what's the limit as x approaches 3? Well, remember, this is where our problem was. If I plug in 3 to the top, I get 3 squared minus 2 times 3 minus 15. So remember this one? Ooh, this is a plus here. It'd be 9 plus 6 minus 15. You get a 0 up top. However, you also get a 0 on the bottom. 3 minus 3 being plugged in gives you a 0 on the bottom. Anytime, if you recall, that direct substitution made this limit approach 0 over 0, that means there is going to be an answer to this. We just need to do some algebra to get it. And in the case of 6, 7, and 8, I think factoring will get us through this, factoring and seeing if something cancels. Let me circle this one. So let's look at the expression. See if you can factor the top. So you've got limit as x approaches 3 up top, so x and x. factors of 15 that add up to 2, so like a 5 and a 3. And maybe making the 5 positive. We've got that thing so that it's factored. Now I look at the bottom and I see a 3 minus x. And this is something that I would really like to cancel. And I notice up top I have x minus 3. Pull a trick. We've done this before in class together. Pick one of these two factors and pull out a -1. That should make this reducible for us. So we've got limit still as x approaches 3 of, I'm going to leave the top how it is. So x plus 5, x minus 3. And the bottom, let's pull out a negative and change both the signs on the inside. So you'll have positive x minus 3 to make those cancel, with 1's left over in their spots. So factoring, reducing, all we have left is x minus 5 over -1. Really, that is just 3. And I should have said plus, 3 plus 5 over -1. So once you get the thing you wanted to cancel to go away, we did a direct substitution to finish the problem. I'm looking at 8 over -1 and calling my answer to 7, just -8. Okay, so we've got some good evens that we skipped on this side, always great to come back to, but I'm more interested in, let's see, as these problems get tougher and tougher, let's see what we can do. 9 looks a little trickier. Maybe give this a try. So it's been a little while. First, decide that there is going to be a solution, right? If I plugged in, just take a second, even pause the video if you want to. Try plugging in 0 for x on the top and bottom. See that you get 0 over 0. So we know there's going to be a solution. After that, let's see if algebra helps us out. I want to make this top. I want to get a common denominator here. We want to give this fraction a 3 on the bottom and top, and give this fraction an x minus 3 on the bottom and top. So we can get a common denominator. And so then we'll be able to read across the top 3 plus x minus 3 over the common denominator. I think it was 3 times x minus 3. And that's all divided by x. So little by little, we're going to get this thing simpler. There's some simplifying we can do up top. Limit as x approaches 0 of, I guess these 3's can go away. So x over 3 times x minus 3. Now watch what I do. This is like a 2 steps in 1. We're dividing by x here. So if you recall, that's the same as multiplying by the reciprocal. So we can write this as times 1 over x and get those to cancel. So this should bring back some memories of times that we've simplified complex fractions to be able to plug in a 0. You'll have 1 over, here's us directly substituting, 3 times 0 minus 3. And I think that'll just be 1 over -9. So see if that'll help. 10, you can get an answer similarly. I feel like with 10, you could do a canceling right off the bat to be able to plug in. But I want to look at something a little bit trickier. Check out this one with the troublesome radical expression. Plugging in 0 gives me 1 minus 1 up top. That's 0 up top and then 0 on the bottom, meaning we got to keep going. I'm hoping there's a little voice inside of your head that's saying, ooh, radical expression, let me try using the conjugate. Lots and lots of times we use the conjugate to simplify and make things cancel in this situation. So conjugate's going to be the same expression you see here with the radical, same signs, except for this middle sign. We're going to change that added or that subtracted radical to an added radical. And we'll do the same thing on the bottom. The biggest part of simplifying here is going to be foiling through up top, because that's the reason you put a conjugate into this problem in the first place. So we're going to try to carefully, we'll go limit as x approaches 0 of this thing foiled. So you've got a 1 times 1. You have, thankfully, with a conjugate, the inner and outer terms are always going to cancel. So plus this root and minus that same root, so no need to write it, minus this root times itself. So just parentheses 1 minus x squared, just what was inside of that radical. All over, just a recopy of the denominator, x times 1 plus 1 minus x squared inside of the radical. I am very hesitant to foil this through. I would rather get rid of this x, get it to cancel. Let's see if that happens in the next step. So we've got limit as x approaches 0 of 1 minus negative x squared. Let's get rid of the 1's and just call it x squared. And on the bottom, I think this will put us in a good situation, because you want to get that x to cancel that was on the bottom, and up top we have just the thing. We could reduce 1 power of x down here with 1 power of x up above. That's all you needed. This is our ticket to plug in a 0 now. we have direct substitution. 1 over 1 plus the square root of 1 minus 0 squared. So you'll have, ooh, and what did I mix up? The zeros on the bottom. How about the 0 for x up top? This should be 0 over 1 plus 1 when you plug in. So 0 over 2 just gives me an answer of 0 there. The last part. You'll notice this final section doesn't have a lot of room for you guys to show your work, because the good news is it doesn't take a lot of work. If I plug into number 12 and directly substitute and get a 1 over 0, negative 4 plus 4, that means I'm getting a non-zero value over 0, and the easy answer is DNE. This was the case where there was no limit. If I look at a graph of this, there's going to be a vertical asymptote at negative 4. And the graph is just, if I look at a limit as x approaches negative 4 from the left and right, there is none. From one side it goes to negative infinity, the other side it goes to positive infinity. And that's because there's a VA at x equals negative 4. Okay. Lastly, let's keep going down the line. I'm noticing 13, 14, 15, and so on. These are all infinite limits, and these are important too. You're looking at, just to refresh this, you're looking at the end behavior of the function, and usually we use HA rules for these. We decide for number 13, is it top heavy, bottom heavy, or balanced? And the HA should be the limit. So I don't know, 13, quick answer, looks balanced, right? X to the first up top, x to the first on the bottom. We pull off leading coefficients. The HA would be 1 over 1. No fancy tricks to worry about. That's just like the HA would be. HA should be the limit. Is 14 looking bottom heavy? Because it is to me, right? You've got a higher power of x on the bottom. Despite the fact that it's approaching negative infinity, I don't really have to think about signs. I'll put bottom heavy for this one. A higher power of x on the bottom. And that HA, if you remember, was always y equals 0. That limit should just be at 0. Okay, now, these last ones, they get a little spicier here. So 15. Oof, x approaches negative infinity. Top heavy, bottom heavy, or balanced? Well, I just have to look at those most influential terms, the highest power you see of x. And to me, this looks like it's top heavy. You got an easy answer for this. Back when we looked for HAs of this, we said there is none. This easy answer for top heavy is DNE. But we can be a little better than that. Can we pick a type of infinity? I'm thinking either positive or negative infinity. I'm not so sure. Well, think of what's really happening. As x gets further and further negative, the top is being raised to an even power and it's staying positive. It's remaining positive. Whereas look on the bottom. The bottom's to an odd power, right? As x gets lower and lower negative, the bottom is approaching negative infinity. I'm going to say as a whole, a positive over a negative gives me negative infinity as another way to give my answer. Both are going to be good. 16 almost tricks you. It looks like it's bottom heavy, but don't be fooled. This x squared is underneath of a square root. It's going to behave like an x. So I'm going to call this balanced. That means pull off leading coefficients. So pull off 5 over 1. But let's think about signs. This thing's approaching negative infinity. The top is getting more and more negative, while the bottom, oof, that's squared, it stays positive. I'm going to call this answer negative 5 instead of positive 5. And last but not least, let's look at 17. I had to put the craziest one. I had to save it for last. Look at what dominates. This is called a transcendental function. It's got trig in it. It's got e to the x in it. You've got a 6x, a cosine, negative 2x, and e to the x. Which one would win in a fight if x were getting bigger and bigger and bigger? Cosine needs to be out of the running. Cosine stays between negative 1 and 1. It's very tame, never gets too big, never gets too small. These two guys are good candidates. They look pretty balanced, but I feel like it's e to the x. That's much more powerful exponential growth. I'm going to wipe out these linear terms. I'm going to say the winner is on the bottom of the function. This is going to act bottom heavy. And for our last solution, an easy answer is just like all bottom heavy rational functions, the limit's going to be 0, just like the HA would be 0. So a little bit curveball in the end, a little bit of practice when you see these infinite limits back with the HA rules, and some good memories of the factoring and the algebra that came with the others. I'm going to leave it up to you to work on the examples that we didn't finish, and I can't wait to hear what your questions are. Until next time, this is Miss Wesley signing out, and I hope that you guys have a wonderful day. Talk to you soon.